In this video, we're going to use Wolfram-Cloud or Mathematica to sort of have some more results on the geometric distribution in probability theory. So this is an extension of a previous video I did where I calculated like the average, the variance, the skewness, kurtosis, and so on. And I did the median. I'm going to sort of follow up the idea of median a little more and do the quartiles. But here's the previous video. Here's the sort of PDF of my session in Wolfram-Cloud. And I also want to shout out to JB Statistics, since I sort of did a refresher of the geometric distribution there before I sort of got started. Okay. So there are my references, the earlier things I did, and JB Statistics. So in the previous video, I found the median, a calculation for the median of a geometric distribution. In a geometric distribution, you have a number of, rounds or events. My example is going to be like rolling dice, and then you'll have some event that you're interested in it the first time that it occurs. So for me, that's going to be rolling two six-sided dice, and I want to know, when do I roll snake eyes for the first time? So that idea of something occurring, you repeating something until some particular outcome occurs for the first time is described by the geometric probability distribution. And as I said, I did a number of other sort of statistical quantities previously in Wolfram-Cloud. Now I'm going to take that sort of median idea and extend that. So I'm going to do the other quartiles. I'm going to do the first and third quartile, sort of find an expression for that in terms of the geometric probability distribution is defined by one parameter, which is P, sort of in a given, in my case, roll of the dice, what's the probability of my outcome snake eyes? So it would be 1/36 for my particular example, but the general, the parameter describing everything is P. So I want to find expressions in P, a generic P, for the first quartile, the third quartile, the interquartile range, which is just a subtraction. And then people typically define an outlier as being 1.5 times the interquartile range higher than the third quartile. There's a corresponding definition of outlier sort of below the first quartile, minus 1.5 of the interquartile range. That's not going to be sort of relevant. That's going to probably be less than 1, and you can't roll the dice less than 1 time. So that only the upper one will be meaningful here for the geometric distribution. I'm just warning that I'm not being, when you actually do quartiles, it's got to be sort of like an integer value, and I'm not going to be very careful about that. So I'm going to get answers that are not integers for things that ought to be integers. I'm going to find the probability of an outlier. Then I'm going to simulate. I'm going to do some Box and Whiskers plots. The previous one, I did some histograms. And then I'm going to sort of compare all the results with the calculations. Okay, so here we go. So the distribution, the probabilities are sort of P times 1 minus P to the n. So you have sort of little n failures, and then you have P is success. So you have a bunch of failures and then success. Okay, and then I'm going up to m minus 1. So this will be, m will be the the mth one will be the success. So we're summing up n minus one. We're going summing n up to n minus one, and that will correspond to n minus one failures and one success. Okay, and I want that to be 1/4. So this is the probabilities, add up all the probabilities until I get to a quarter. I'm going to take that as the sort of the first quartile. And so then I just solve that. So I get this expression. I can take I see I have like, when I did solve, it had like this double curly bracket around it. I can get rid of that. Square brackets are usually a function thing in Mathematica. So if I want to use more of like an array type idea, or then I need sort of double square brackets. And to get rid of like two sets of curlies, I need square bracket one, square bracket one. That's going to be m arrow the thing. And then if I want to get rid of the m arrow and just have the expression, then I say values. So that's just a lot of notational things here, but to sort of extract that solution, that's what I'm doing here. Okay. So now play the same game, but I'm adding up all the probabilities until I get to 3/4 for the third quartile. There we go. And then play the same game with the double square bracket ones repeated and values to get this sort of value. The value has a variable in it. And okay. So next I'm going to get the interquartile range. So that'll be just simply, and that's why I want to get rid of those sort of m's up there, because I want to, do a subtraction and multiply by 1.5. So I'm taking the third quartile minus the first quartile times 1 point. So that is actually wrong. That's not the definition of interquartile. Let me fix this here on the fly. The quartile is just the Q3 minus Q1. And then the outlier bound, I'm calling it here, that's where the 1.5 comes in. Sorry about that. So the interquartile range is just the subtraction of Q3 minus Q1. Then the bound between where we start defining outliers is Q3 plus 1.5 times the IQR. Okay. And then again, there is, and for most distributions, there's a corresponding Q1 minus 1.5 IQR, but I'm pretty sure that will be less than 1 and sort of not relevant for this geometric distribution. Okay. Now I'm going to return to my geometric probabilities of p times 1 minus p to the n, and then I'm going to here's the one place where I'm going to be careful about integer values. I'm going to take the ceiling of that outlier bound, and then I'm going to start there and go up to infinity. And so I'm adding all the probabilities that are higher than this outlier bound. And so this is overall the probability of there being an outlier. Okay. Now I'm just going to, so all this was in terms of the parameter P. Now I'm going to put in a particular P, and then I'm going to do a simulation. So this is the P that will be relevant to my simulation below, and that's P of 1/36. So I can put in the parameter of P is 1/36, and then get the numerical value for my first quartile. So 10 or 11, depending on how you're going to play the ceiling or floor kind of a game. The third quartile, the interquartile range. Now I took out that 1.5. I'm going to get a different value here, but then the outlier bound should come back and be the same. Okay. And then the outlier bound. So this is that value for which above that value, I should start designating them as outliers. And this, I didn't do that right, Shift Enter. Okay. And the geometric distribution tends to have a fairly substantial tail. Um, so we will see a number of outliers. Okay, and so this is our probability of an outlier. And it was, not quite 5%. Okay, for this P of 1 on 36. Okay. I'm just clearing P in case I want to do anything later, get my P's back. I don't think I do, but just in principle. Okay. Now here is my simulation. Let's look down at the while method. While my sum is not equal to 2, just typing wise, I hit exclamation equals for not equals, the standard sort of computer science equal, which Mathematica Wolfram-Cloud turned into a not equal sign. While the sum of the two die values is not 2, I'm going to get two new values using random integer, die1 and die2. I'm going to add them. I'm going to increment a counter, which is not counting up the number of times a roll. And I keep counting while I'm in the loop. I get out of the loop when I roll snake eyes. I have a sample number of 10,000. I have my samples is an empty list to start off with. When I'm done my while loop, I will add my count to samples, and then I will take my sum back to 0 so that I get into my while loop. I'll take my count back to 0 because it's the next sort of sample. Okay. And so pretty quickly, it gives me 10,000 samples of that. And as I say, in the previous video, we did some histogram stuff. Another standard chart of such things is the box and whiskers. So here is a box and whiskers. So we see this whisker above is quite long. And I'm going to look at the quartiles. So part of this is described by the quartiles. So 11, 25, 49. Let's have a peek at what we got above. I don't think I got the median. I got it in the previous video, but I didn't do it here. But 11 and 49, and 49. So we have doing pretty well in our calculations versus our simulation. Now, there are different ways of showing a box and whiskers. So in this first version of the box and whiskers, this sort of I-frame type thing at the top extends all the way to the maximum. But when you have outliers, a different way that box and whisker plots are sometimes drawn is that this is sort of the bound of the sort of the highest one that's not an outlier, and then the outliers are drawn as dots above. That's sort of another standard way to make a box and whiskers plot of data with outliers. And you can just sort of get that by adding box whisker chart and then the samples, my list of data, and then I put in the word outliers in quotes. And that got me this one, and we can see that this, it gives you the quantities, the min, the 25, the first quartile, the median, the 75, and then it gives you all the way to the max. But this line you can see here is roughly of like around 100. And so that is that borderline, so that we found above for the outliers. Okay. Now let's do it for the simulation. We did it above, like calculation-wise, but let's do it for here. So I have I called the quartiles QS. There are three. The first, second, and third quartile. Middle quartile, the second quartile is, of course, the median. I'm taking Q3, again, the square bracket notation, QS3 minus QS2, that's the interquartile range, IQR, multiplied by 1.5 and added to QR. And I'm getting 106. Again, now I'm in the simulation part, so the answer jumps around a little bit for different randomness. Okay. Now I want to use the sort of select method, and I want to pull out the outliers. So I'm going to select from the samples elements where the number, the value, is greater than the sort of upper bound for quartiles. And then you need this little and at the end. It wasn't working without it, so you need it, but I don't quite know what it does, but you need it. And then I'm defining that as the outliers. So here's my big list of outliers. And then I'm going to use the length. So I'm going to do the length of the outs, count up how many outliers there were, divided by the length of all the samples. And then I didn't want it as some rational fraction. I wanted just the numerical value. And so I put an n around it. And there's my sort of about 5%. And again, how are we comparing? The probability in terms of P for an outlier was about 4.77%. And then down here for this particular simulation, I got about 5%. So we're doing reasonably well. Okay, so that's what I wanted to show you. Add in first and third quartiles and the idea of outliers, and move over from previously we did histograms, move this time to box and whisker plots. And that's all for this one. Thanks for your attention.